Okay, and so that's our connecting link that gives us the velocity. We can get the period from the time between the peaks. But we get the velocity from the distance from 0 to 0.09 in this amount of time. And so that's how you get the velocity moving to the right, 0.09. And then here, this looks like about 0.035. Although some people might argue with that. Anything close to that, you get full credit for. That would give us the velocity to the right. Once you have that, then you know the frequency, and so you can get the wavelength. Okay, and so the wavelength then is 0.144 when we're traveling to the right. Well, what about to the left? Well, to the left, as you decrease in x, you're increasing in time. So it actually represents a completely different wave. And that wave is not the same as the wave that's traveling to the right with just a flipped sign. It is a completely different wave that's being represented. And so when you go from x equals 0.09 to 0, we do it over a shorter period of time, and so therefore the velocity is higher. Okay? And then once we have that established, then then you can go ahead and figure out what the wavelength is, and so that's going to be the velocity divided by the period you get from that time differential. And so then you can write your equations traveling to the left and to the right. But notice here there's a different wavelength because there's a different velocity for traveling to the left and to the right. Now what I'd like you to do with this is to see if you can find the phase angles. So I'll let you do that for extra credit. Also, I wanted to mention on the quiz that's coming up Thursday, I'm going to get that back, and then we have a midterm a week from Thursday. And so what I'm thinking is I'll postpone collecting the homework for this Thursday so that you have to study from. I don't want to have it over the weekend when you could be studying from it. You won't take this as a sign not to do the homework. Because the quiz on Thursday, it'll be 10 problems, 4 points each. So it's kind of like a little mini midterm, not quite, maybe 4/10 of a midterm, which is the same as how our first quiz was. So the quizzes count for a lot. You add the two quizzes together, that's like 80% of the midterm. Okay, and so that is what I wanted to talk about there. I did pass out the solutions to this one that anybody that wants to look at it in more detail after class is welcome to. And then the solutions here are for our first group quiz, first and second group quizzes. And then this is our group quiz for today. Any questions? Yeah.
I noticed that we weren't able to see our past pre-lab quizzes. Like once we did the quiz, if we like looked back at it, we couldn't see all the questions and like the answers.
Okay, I've got to go through it and open that up. I wish that they would. There's like 10 things that you have to do before the thing opens up. That'll all fix that for you.
Yeah, I thought it'd be good study material.
Yes. Okay. So let's go ahead then and look more at refraction today. Now on the quiz, expect maybe 7 problems out of 10 from chapter 17 and maybe 3 out of 10 from this new stuff that we're covering. Okay, and it'll be fairly basic. from the new stuff because we're kind of just getting into it now. Okay, so last time we were looking at different kinds of reflection and refraction, and we had established that for the law of reflection, let's fix this here. For the law of reflection, the angle of incidence always equals the angle of reflection. But we have to be sure that we're talking about this with respect to a normal to the surface. So in specular reflection, we get a well-defined representation of the original light. Whereas in diffuse reflection, say we had a ripply surface to a pond, then you would get a distorted image. And then what we had just finished with last time is this idea that some of the ray energy can bend. Okay, so some bounces, there's a reflection, so that the angle of incidence equals the angle of reflection. But some bends goes through this way. So this is the original direction of the ray, but notice the ray bends toward the normal. So if I call this theta 1, then this angle here would be theta 2. And this is when we go into a more dense medium, the light rays bend toward the normal. Now down here, let's say that this is N for water. Although it's a plastic here, let's just say it's N for water, because I know the N for water is 4/3. And this would be the N for air, which is about 1. Okay, remember our definition for index of refraction is that it's equal to the speed of light in a vacuum divided by the velocity in the medium. And remember that the velocity in the medium is going to be less than the speed of light. So in order for there to be a velocity in this medium, it must be a transparent medium. Otherwise, the light wouldn't go through at all. But it has to be able to let through light, but it slows the light down. And so we could then, if this were in fact water that it was bending into, we could do a quick little calculation for the velocity of light through water. We could do that just by saying V is equal to C over N. Remember that N must be greater than or equal to 1 because V is less than or equal to C. Okay, so the index of refraction, as it gets bigger, we get a slower and slower velocity. And so this is usually representative of a more dense transparent medium. In a more dense medium, you get an induced wave that's produced by the electrons being excited within the medium, and that interferes with the wave that's coming through. That gives rise to a composite wave that's traveling slower than the speed of light. Okay, so in this case then, this would be 3 times 10 to the 8 meters per second divided by 4/3. So that would be 3/4 times 3 times 10 to the 8, or 2.25 times 10 to the 8 meters per second. So we're at 75% the speed of light when the light is traveling through water. Now, because of this bending effect, we can again picture this to be like what happens if one part of the light ray comes in before the other part does. You can think of these as being like plane wavefronts. These are rays, but then think of these as being like peaks of the wave. So the wave is actually doing this kind of thing as it's moving along, but we're just looking at the ray. So this part of the wave gets in first, slams on the brakes, and then the other part has a chance to kind of catch up and bend. And so that's what physically produces the bending. We went through a little exercise with calculus last time, that's on that handout I gave you, that verifies that this is the relationship for the path of least time. N1 sine theta 1 equals N2 sine theta 2. This is called Snell's law, path of least time. So this bending of light can produce some very interesting visual effects. Any questions so far? Okay, here's a table of the index of refraction for different transparent media. So we can see then that we would expect with a higher n value, we would get a lower velocity and therefore more bending. So we get more bending with higher n values, and then this drops down to like water, 1.33, which is 4/3. Okay, and so each of these substances then is going to have a little bit different bending properties for the incident light. All right, so let's go back to that original example. And let's say that the angle of incidence here is 30 degrees, and this is in air. And air is approximately equal to 1. Now it's a little greater than 1, just slightly greater, but the decimal places, you've got to go out 3 or 4 decimal places to see that it's much different than 1. And so to a good approximation, we can just always call the index of refraction through air 1. And then in water, we're using water, 4/3 or 1.33. And so we know there's going to be some bending that's going to bend toward the normal. When you go into a more dense medium, light bends toward the normal. And that just means that theta refracted gets smaller. If it's bending toward the normal, here's the normal. Remember, the normal is just our perpendicular construct that we measure all our angles with respect to. And so if this is 30 in air, then because it's bending, that angle has to get smaller. And so that's bending toward the normal. Okay, so that's our general picture that we want for this kind of a process. And so if we're given this information, let's find theta r. Okay. So we can get that then by just saying 1 times the sine of 30 equals 4/3 times the sine of theta. And that gives us then sine of theta equals sine of 30 is 1/2. So then that would be 3/8. Or theta is the inverse sine of 3/8. It's around 21 degrees or so. .02. Now, we can't tell right off the bat whether this is the right answer, but we can certainly tell if we've made a fundamental error. Because if we found an angle that was greater than 30, we'd know that that couldn't be right. And we know that it's probably going to be a pretty good bend because it's only traveling 3/4 as fast through water. So, although we can't say that this is absolutely correct, we can say that it perhaps is in the right ballpark for that kind of a calculation. Okay, so it's just basically one equation and one unknown, but we just have to know how to represent each of those quantities and then to solve for the unknowns. Okay. Now, if we're going into a more dense medium, it bends toward the normal, but it makes sense then that if we're going into a less dense medium, we bend away from the normal, or theta gets bigger. That's just the reverse. Most things in physics work fine in reverse. Here we're moving along, then this side slams on the brakes, this side doesn't, bends that way. If we're going this way, then this part comes out faster on this side. Think of these as being like wave fronts, and these as being like many waves. So as this wave front comes in, this part of the wave front comes out first, starts going faster, and so it does the reverse. It bends away from the normal. Okay, now, what if we had parallel pieces of glass, and the light goes through both? So it goes in and then back out again. Well, if that's the case, then there should be no net deflection, because the amount that it bends going in should just be compensated for by the amount that it goes back out again. And so basically, this is what happens when light goes through your window. You don't see a distortion of the light. You see a slight displacement, but what would you have to measure that in reference to? So you're not going to notice that. It's going to look pretty much the same, although you may look at the light as not having quite as much intensity, because maybe a little bit of that light energy could be lost in the form of heat or other types of processes that can go in that in that substance. But we would expect that the amount that it bends toward the normal going in is going to just compensate for the amount that it bends away from the normal going out. So theta 1 is equal to theta 3, and these rays are parallel.
That's for two parallel glasses, right? Or like,
Yeah, as long as they're parallel surfaces,
okay.
then that'll work. If they're not parallel, then there'll be some net amount of bending that'll take place, and so that'll be when we get into lenses, is when they're not parallel.
And when they are parallel, it'll be theta 1 is equal to theta 3?
Yes.
Gotcha.
Yeah, because the amount that it bends going in is the same as the amount that it bends going back out. So by symmetry, these angles have to be equal, so therefore that angle is equal to that one.
Gotcha.
Any other questions? Okay, now, next I wanted to look at what happens if you look at an object in a more dense medium. Okay, so in this case, we might be, say, in water, and then here, this might be where you're viewing. So let's just put a big eye here. Looking down along that path. Okay, and so what's going to happen then is that each of these beams of light is going to bend away from the normal, because it's going from a more dense medium into a less dense medium. But then an extrapolation along those straight line paths will give rise to an illusory source of light. Not really there. But it looks like it's coming from there, because all your eyes have ever evolved to do is extrapolate along straight line paths to the apparent source of the light. So if that's the case, let's say this is a fish here, then here we would reconstruct point by point a virtual image of the fish. And when we do this, we find that the magnification, this is something that I'll show a little later on, that the magnification is just equal to the ratio of the indices of refraction. So we get about 1/3 magnification, because it's 4/3 divided by 1 for the ratio of the indices of refraction. So because it looks closer, it takes up more what we call angular size, so therefore it looks bigger, because it's taking up more of an angle when you look. And you see it's not really that much bigger, but that is what it looks like. And so there's no real source of light coming from that location. And the same sort of thing would be true if you're snorkeling and you're looking at fish underwater. You go, wait a minute, how does that work? Then you've got a faceplate that are two parallel pieces of glass. Well, true, but let's say that this is the actual source of the light here for the fish. So that light comes in, and then once it goes through these two parallel faces, it's still parallel to the direction that it had bent originally. So it's not a contradiction to say that it bends here, because the light that comes out along this path is going to tend to bend away from the normal, because it's going from water into air. Here's your eye looking at it. There's your nose down there, mouth. There's your faceplate. And so what you do then is you extrapolate along straight line paths, and then you see the virtual image of the fish here. And so when you're looking underwater at a fish, you're seeing the same magnification factor that you see if you're looking at the fish from above the surface of the water. There's this bending effect, because there's two parallel surfaces. It's just the bending effect that you would get from one surface, essentially. And so this again is your virtual image. Now, if you were to look, for example, at the sun, here's another example of a virtual image. And you see the sun just above the horizon, maybe with just a little bit of it poking above the horizon. You'd say, well, the sun is setting. But no, it's actually already set. So what tends to happen here to produce this virtual image of the sun at sunset is that these layers of air have different densities. And it goes like an exponential drop-off. If you had me for 2AA, you saw that it looked something like this. P naught e to the minus mgy over kt. So there's an exponential decrease in the pressure with elevation above the surface. And so what that does then is that makes the air closer to the surface more dense, the air farther away from the surface less dense. Okay, so you're going from less dense to more dense. So you can imagine this happening in a series of little bends toward the normal, like that. And, it's coming from here. So you can see it along these lines as being little bends toward the normal. And then here you are looking, and you extrapolate along straight line paths to the apparent source of the light, and you see the sun still above the horizon. So you actually, in reality, get a couple of extra minutes of daylight in the morning and in the evening because of the refraction of light through the Earth's atmosphere. So it bends it something like what a lens does. And then this is your virtual image of the sun, which still looks like it's above the horizon. So we see that there are a lot of light tricks that have been going on that we have evolved to try to make sense of over millions of years. And so virtual images are important because it's where the light seems to be coming from our point of view. But by definition, it's where no real source of light is coming from. Any questions so far? Okay, now let's just go back for a second to mirrors. When we're looking at mirrors, what you tend to look at is a reflection of yourself where the virtual image seems to be on the far side of the mirror. So if you're standing here, looking at yourself in the mirror, and this distance is d, let's say you're looking at the light that's coming from your foot. So some of this light will come up along that angle. Some will be expanding away, because from each point, we can think of the light as moving away from that point along different ray paths. Okay, and so if this comes in a little sharper, like that, or a little farther away, then those rays are going to get farther apart by the time that they get to your eyes. And so what your eye does then, I'm making the eye really big here, because these rays can actually be quite a bit smaller, so that it actually does correspond to the size of your eye, is you extrapolate along those straight line paths to the apparent source of the light. And this produces a virtual image of you on the other side of the mirror. And because the angle of incidence always equals the angle of reflection here, the size of the virtual image is the same as the size of the real image. This is the real source of light. This is the virtual image down here. And then you can do that point by point throughout your body. You can do it from the knee. And that would come up like that. Then another one would come up, be spreading out a little more. And so the extrapolation, sorry, coming from here, then up to your eyes like that. And we extrapolate, and I draw carefully. You could represent every point on the light source as being, by an extrapolation, some kind of a virtual image that is on the other side of the mirror. So oftentimes in a small room, you'll put a mirror in there so that things look bigger. It appears as though you've got a bigger room because you're actually focusing on a point that's equal distance on the far side of the light source from where you're at. Now, what if you had several layers? Let's say this is N1, N2, N3, N4, and N5. And then this is N6. Let's say you have the light coming in like that, bending there, and let's say that N6 is greater than N5, is greater than N4, greater than N3, greater than N2, greater than N1, greater than N0. Would we have to do all the Snell's law calculations here? Let's say that we were told that this angle was 30 degrees, and this N0 was 1 for air. Then let's say N6 was 4/3. And all the rest of these indices of refraction were intermediate values between 4/3 and 1. You think that our fastest solution here is going to be to do each one of these as a separate calculation if we want to find theta?
You just do N0 to N6.
Yeah, you could just skip over. You could go from N0 to N6. Why? Because N0 sine theta 0 equals N1 sine theta 1. But then here in this one, this is theta 1. This is also theta 1. So you'd have N1 sine theta 1 equals N2 sine theta 2. And you'd have N2 sine theta 2 equals N3 sine theta 3. So you go all the way down, all these cancel until you get down to the bottom, N6 sine theta 6 is equal to N5 sine theta 5. Okay. And so all of these side terms cancel, and so when you add all of these together, you just get the same thing that we got in our first example, which is just the bending of light when it goes from 30 degrees to 22 degrees. And so it's possible then to avoid a lot of these intermediate calculations if you have a bunch of parallel layers by just looking at what the angle of incidence is at the top layer, what the angle of refraction is from the bottom layer. Any questions about that?
Would N6 ever be not given? And,
Well, then you wouldn't have enough information to solve. So you would need to know that, yeah. But you wouldn't need to know any of the other ones. I mean, this one could go up, this one could go down, up, down. They'd still cancel when you write them out like that. And so you would only need information from the top and the bottom layer, as long as they're parallel layers. Any other questions? Okay, another kind of problem that we can look at is what's called total internal reflection. Now, there we go. This was the virtual image from the mirror. And we'll come back to that. But what I wanted to do next was look at the principle of total internal reflection. Now, in total internal reflection, what you have essentially is light that goes from a more dense medium